In this example, an IVF institute claims that they have a method that is designed to increase a person's probability of conceiving a girl, and they call this method the XORT method. So they claim that if you use the XORT method, it will increase your chances of conceiving a girl. So we want to know, what is the probability of actually conceiving a girl when using this XORT method? So to estimate for P, we'll take a look at a sample, and that sample comes from a clinical trial done by this institution. So this IVF Institute does a clinical trial where out of 325 babies who were born to parents using the XORT method, so I'm going to start writing down all the information as I'm reading it. So here, because this is a sample, a clinical trial, 325 is our sample size. And then X here represents the random variable for births that are girls. And here in this clinical trial, we're told that 295 births are girl births. And so from this information, we can calculate our sample proportion, which is the proportion of births that are girls. And so to calculate that sample proportion is always X divided by N. So 295 girls out of 325 births using this XORT method leads us to a sample proportion of 0.908. So this says that this clinical trial shows that approximately 91% of births using this XORT method resulted in girls. So that's a pretty high probability, because if parents were not using any method, then I hope you would agree with me that the probability of conceiving a girl is 50% or 0.50. Okay, so we want to know, is P really as high as our sample proportion P hat of 0.908? So to find out, we are going to we're going to compute a 99% confidence interval to estimate for P. So to calculate this confidence interval, there is a formula, okay? And before I give you this formula, I need to talk about a vocabulary word that's really important, and that is the margin of error. Okay, so I'll write it at the top here. A margin of error, which we call E, right, measures the difference between your sample proportion and the actual population proportion. So it basically measures your error, okay? So when we estimate for P using P hat, right, what is the actual difference between P hat? So what is the difference between P and P hat? That's our margin of error. Okay, and so to calculate the margin of error, the formula that we use, so to calculate E, is we have to get a critical value. So alpha divided by 2, this is called your critical value. And I'll explain what all the pieces mean in just a second. And we multiply it times the square root of P hat times 1 minus P hat divided by your sample size. Okay, so to get E, we need to find our critical value. So Z sub alpha is a z-score on the normal distribution that separates, right, very, very high z-scores from the rest of the distribution. So to calculate this critical value, which we call z sub alpha divided by 2, if you're using your calculator, you want to use inverse norm. So what on earth is alpha? In this problem, if we want to compute a 99% confidence interval, so I'm going to call this C level, which means confidence level, and we always write this as a decimal. So if our confidence level is 0.99, then alpha, right, is 1 minus your confidence level. And so in this particular problem, alpha is 0.01. So 0.01 represents our error. And when we're building a confidence interval, that error is displayed in the tails of this normal distribution. So the total shaded area in the left and the right that I've shaded in red, those two red shaded regions in the tails add up to alpha, which means that each tail has an area of alpha divided by 2. So in this particular problem, if our confidence level is 0.99, 0.99 represents this white shaded region between the two red shaded regions in this bell-shaped curve, then that means that the area of the red shaded region is going to be 0.01 divided by 2. Okay, and so the area of each tail, so this red shaded region has an area of 0.005. Okay. All right, so there's a lot of work that we have to do here to get to our critical value. So to find your critical value, I'll write it up here. We want to find z sub alpha. So alpha in this problem is 0.01 divided by 2. We're going to use inverse norm. So inverse norm is going to give us the z-score that separates this red shaded region here from the rest of the distribution. So you can just type this into your calculator. You can type in 1 minus 0.01 divided by 2, and your calculator will do that calculation for you. And then we type in 0 for mu and 1 for sigma. And when you press enter, your calculator will tell you that that critical value is approximately 2.58. Okay, so that's the value that we are going to use to put into this part of the equation here to calculate our margin of error. All right, so let's go ahead and calculate our margin of error. That's 2.58 times the square root of p, so p hat, which is 0.908, times 1 minus 0.908, and divide that by our sample size of 325. And that's going to give us a margin of error of approximately 0.041 if we're rounding. Okay, so to write your confidence interval, there are 3 ways that you can write your confidence interval. You can write it as p hat plus or minus your margin of error. This is the most common way that confidence intervals are written in print because it's the shortest notation. Or you can write it as p hat minus e is less than the population parameter, which is less than p hat plus e. So here, p hat minus e is your lower limit, and then p hat plus e is your upper limit. And I mean lower confidence limit and upper confidence limit. And then the third way, which is the most common way that students write it, because this is how your calculator gives you the confidence interval, is to write it using these open parentheses, where the first number that you write is your lower confidence limit, which is p hat minus e, and then the upper number is your upper confidence limit, which is p hat plus e. Okay, so we just found e, we know p hat, and so now let's put it together. So we're going to start with p hat minus e less than p hat plus e. So let's put that together. So our p hat 0.908 minus 0.041 is going to be less than p, less than 0.908 plus 0.041, which gives us a confidence interval of 0.867 up to 0.949. Okay, I know I kind of squeezed it at the bottom there, but let's interpret this confidence interval. So this confidence interval tells us this. It says that we are 99% confident that the population proportion, meaning that the proportion of births that are girls using the XORT method, is anywhere between about 86.7%. So it could be as low as 86.7% and as high as 94.9%. And since these percentages are relatively high, we can assume or we can interpret it that the XORT method is effective in increasing your chances of conceiving a girl, because if you don't use the method, your chances would just be 50%. And our confidence interval here says that we're 99% confidence that the XORT method will increase your chances of conceiving a girl up as high as 95%, so approximately 94.9%.